Hello. In the previous clip we looked at Fourier transforms and how it helps us to obtain the impulse response of a system without applying an impulse input. But then in the process we discovered that the mathematics of Fourier transforms allows us to transform a convolution integral, which is what we need to solve in the time domain to obtain the response of a system to any particular input, to a product. So the Fourier transform of the response is equal to the product of the Fourier transform of the input and the Fourier transform of the impulse response. Now since a product operation is significantly more intuitive compared to a convolution integration operation, we saw some benefits in not analyzing systems in the time domain, but rather by sticking to the frequency domain itself for our design and analysis purposes. However, as control engineers we discovered that despite all the benefits of Fourier transforms in terms of increase of intuitiveness and so on, it still has drawbacks in that there are some signals which are of great relevance to us as control engineers which do not possess Fourier transforms. So we gave the examples of a ramp function, an increasing exponential, all of which do not possess Fourier transforms, and other functions such as the step function or sinusoidal input which have delta functions in their Fourier transforms are rather difficult to deal with, and these once again are signals that are very commonly encountered in the course of control system design. And that led us to investigate if weighing down such functions with decreasing exponentials would allow for such functions to possess Fourier transforms, and while we proceeded down that path we came upon the definition of the Laplace transform. So what I have shown here in this slide is the expression for the Laplace transform of a signal u of t. It is given by capital U of s is equal to integral from 0 to infinity u of t e power minus st dt. It is assumed that the signal u of t starts at the time t equal to 0. In order to highlight the unity in our quest for representing signals using different elementary functions, I have shown in this slide our attempt so far. We started off by representing our signal in terms of impulses. So that led us to this particular convolution integral where we represented u of t as a train of impulses delta of t minus tau. But this we discovered had problems because delta was a spiky function which could potentially damage our system. So we tried to represent u of t in terms of other more benign functions, and this was what was accomplished by using Fourier transforms. We were able to represent u of t once again, this time not in terms of delta functions but in terms of complex exponentials e power j omega t. So just as in the previous case, delta of t minus tau had to be taken in the proportion u of tau times delta tau and added up to get u of t. Here we had to take any specific complex exponential e power j omega t in the quantity u of j omega times d omega and add it all up to get u of t. And that quantity or the frequency content of the signal u of t we called as the frequency spectrum, and u of j omega which was also called the Fourier transform of u of t, and that was given by this particular expression here. Now what we have managed to do is to represent u of t not in terms of complex exponentials e power j omega t but rather in terms of complex exponentials e power st. The reason we had to do this was because there were a few signals of great interest to us which could not be represented by using the mathematics of Fourier transforms. So by replacing j omega by the term sigma plus j omega which we defined as s, we were able to represent a bigger set of signals including those that are of importance to us by using the complex exponential e power st. And the quantity once again of each of these complex exponentials e power st that we need is characterized by the terms u of s times ds. So therefore you see that in each case we have attempted to represent u of t in terms of elementary functions, delta function in the first case, complex exponential e power j omega t in the second case, and e power st in the third case. And what you also see is this interesting similarity between Fourier transforms and Laplace transforms, in that in Laplace transforms we have S to be equal to sigma plus j omega. So in the case of Fourier transforms we have e to the power j omega t, where omega is a real number, a real frequency, whereas in the case of Laplace transforms I can write e power st as e power j times omega minus j times sigma times t. So what we notice is that if we replace a real frequency, namely e power j omega t, a real frequency omega, by a complex frequency omega minus j sigma, we will essentially transition from Fourier transforms to the Laplace transforms. So having justified the usefulness of Laplace transforms for control engineering purposes, let us now examine some of the important properties of Laplace transforms. Now the first couple of properties that I want to talk about are whether Laplace transforms exist for all signals u, and for those signals for which it exists, does it exist for all values of s. So to answer the first question, Laplace transforms actually do not exist for all signals u. For Laplace transform to exist, in other words, we should be able to get a finite value for this integral 0 to infinity u of tau e power minus st u of t e power minus st dt. This happens if only the signals u of t are of exponential order. What we mean by this is that we should be able to find a time t naught beyond which the magnitude of this function u of t can be bounded by a term of the kind k e power c times t, where k is a constant and c is a constant. If a function u of t can be bounded by a function of the kind k e power c times t, where k and c are constants beyond the time t greater than or equal to t naught, then such functions are said to be of exponential order. And it is easily verifiable that not all functions are of exponential order. So if you take for instance a ramp input u of t equal to t for t greater than or equal to 0 and 0 for t less than or equal to 0, t less than 0, then you can easily show that the value of c here can be arbitrarily close to 0, and yet I will be able to bound u of t by using such a value of c. Likewise if I have a complex, if I have u of t equal to e power at, then I can bound this function by choosing a c that is greater than a. So even increasing exponentials are of exponential order. However, there are other functions that are not of exponential order. For example, if I take a signal of the kind u of t is equal to t to the power t, or u of t is equal to e to the power t square, these are all signals that are not of exponential order and for which the Laplace transform integral will not exist. In other words, it explodes. So we cannot define Laplace transform for signals of this kind, but fortunately for us, signals of this particular form are not commonly encountered in control system design and practice, and hence it is not of great concern to us that we cannot define Laplace transforms for these signals. The second question is, does the Laplace transform exist for all values of s? In fact, you can show that if you take the simple example of u of t equal to e to the power at, then u of s is equal to integral 0 to infinity e power at e power minus st dt. You can clearly see by inspection that if the real part of s is less than a, then you would have an increasing exponential on as the integrand, and therefore u of s cannot be defined. Therefore the real part of s has to always be greater than a for this integral to exist, and this can be observed even in case of other functions. So, there are only certain values of s for which u of s results, for which the integral converges, and this set of values of s is called the region of convergence. So, it is only within the region of convergence that the Laplace transform of the signal is defined, but not outside it. Having looked at the fact that Laplace transforms firstly cannot be defined for all signals u of t, and secondly does not exist for any possible value of s, we shall now look at the Laplace transforms of some common signals. So, let us first take u of t is equal to delta of t. Computing the Laplace transforms is a straightforward activity where we simply evaluate the integral u of s is equal to integral 0 to infinity u of t e power minus st dt, and if you do it for the case of u of t equal to delta of t, you get u of s to be equal to 1. So, this is the first signal. One other common signal is u of t equal to 1 for t greater than or equal to 0 and equal to 0 for t less than 0. This is called as a step input. This is also often called as a Heaviside step, and it is given a unique symbol, it is called 1 of t. So, what is the Laplace transform of 1 of t? You can show that the Laplace transform of 1 of t is given by 1 by s by simply computing this particular integral. Third is a sinusoidal signal sin omega t, sin omega t times 1 of t, because we are looking at signals that are starting only at time t equal to 0, and for this we can show that u of s is equal to omega by s square plus omega square. Likewise, if you have cos omega t times 1 of t, u of s will be can be shown to be equal to s by s square plus omega square. How about exponential functions? So, if I have e to the power a t times 1 of t, I can show that u of s is equal to 1 by s minus a. But once again, all these Laplace transforms have to be qualified by stating that these are the values of the Laplace transforms within the region of convergence for these particular signals. So, what is the region of convergence for a step input? You can show that the real part of s should be greater than 0, and which represents in the complex plane the entire of the right half of the complex plane. So, this is the region of convergence for a step input. Likewise, also for sinusoidal input, you can show that the region of convergence is real part of s is greater than 0. For an increasing exponential, however, you can show that the condition is that the real part of s should be greater than a. Likewise, if you have a decreasing exponential, so e to the power minus at 1 of t, where a is greater than 0, you can show that u of s is equal to 1 by s plus a, but once again within the region of convergence real part of s greater than minus a. So, these are the Laplace transforms of some of the commonly encountered signals. Let us now look at some of the general properties of Laplace transforms that are applicable to all functions for which we can define Laplace transforms. One is the property of differentiation of the signal. How is the Laplace transform of the time derivative of a signal, namely du by dt, how is the Laplace transform of du by dt related to the Laplace transform of u of t? So, how are these two related? So, you can show that if the Laplace transform of u of t is equal to u of s, then the Laplace transform of du by dt is equal to s times u of s minus small u of 0. Small u of 0 is the value of the time domain signal u of t at the time t equal to 0. So likewise you can generalize this further. If you have d square u by dt square, the Laplace transform of d square u by dt square, I will represent L of du by dt as a Laplace transform of du by dt. So likewise a Laplace transform of d square u by dt square is equal to s square u of s minus s times u of 0 minus u dot of 0. So this is something that you can show as well, and so on and so forth. Likewise if I have any signal u of t, can we derive the Laplace transform of integral of u of t in terms of the Laplace transform of u of t? It is indeed possible to do this. So we do this by computing the Laplace transform of integral u of t dt as integral 0 to infinity integral u of tau d tau, the upper limit of this integration being t e power minus st dt, and you can show by integration by parts that this is going to be equal to u of s by s minus u inverse of 0 by s, where u inverse of 0 represents the antiderivative of u at time t equals to 0, or in other words it is integral up to time t equal to 0 u of tau d tau. This is equal to u inverse of 0. Next is the convolution. So if x of t is equal to integral 0 to t u of tau g of t minus tau d tau, what is the Laplace transform x of s in terms of u of s and g of s in terms of the Laplace transforms of the input and the impulse response? You can show using mathematics very similar to what was employed in case of Fourier transforms, that x of s will be equal to u of s times g of s, or in other words g of s, which is the Laplace transform of the impulse response, is a ratio of the Laplace transform of any response of the response to any input x of s divided by the Laplace transform of the input itself, namely u of s. So this term g of s, which is the Laplace transform of the impulse response, plays as important a role in frequency domain and Laplace domain analysis as the impulse response itself plays in the time domain. So there is a special name for g of s, it is called the transfer function of a system. Having defined the transfer function, let us look at how the transfer function appears for a system that is of interest to us. So to remind you, the system that is of interest to us is a system with governed by an nth order differential equation relating the output to the input. So d nth derivative of x with respect to time plus a1 times the n minus 1th derivative of x with respect to time, and so on and so forth, plus a n x is equal to b1 times mth derivative of u with respect to time, and so on and so forth, plus bmu, with n initial conditions x of 0, x dot of 0, and so on and so forth up to x n minus 1 of 0. So we are interested to obtain the transfer function for the system. So we are therefore exclusively interested in focusing on the input output relationship. So for the sake of simplicity at this point, we shall not consider the effect of the initial conditions, and we shall set all these initial conditions to be equal to 0, so that we do not have to carry them over in our calculations and in our quest to obtain appearance of the transfer function for this system. So with all the initial conditions equal to 0, I shall now apply Laplace transform both to the left hand side as well as the right hand side of this equation. So I apply the Laplace transform of this, and that should be equal to the Laplace transform of that, Now Laplace transform of nth derivative of x with respect to time when the initial conditions are 0 is simply equal to s power n times the Laplace transform of x. Similarly, for any other index, Laplace transform of n minus kth derivative of x with respect to time can be shown to be simply equal to s power n minus k times the Laplace transform of x. So utilizing this fact, we can write out the Laplace transform of the terms on the left hand side to be s power n times x of s plus a1 times s to the power n minus 1 times x of s plus and so on and so forth plus a n times x of s to be equal to b1 times s power m times capital U of s, where capital of U of s represents the Laplace transform of u of t, plus so on and so forth up to bm times u of s. So if I were to simplify this expression, I can take out x of s from this from the left hand side and write this out as a polynomial in s. So s power n plus a1 s power n minus 1 and so on times x of s will be equal to b1 s power m plus and so on and so forth up to bm times u of s. So what we would get is therefore that x of s by u of s is equal to b1 s power m and so on and so forth up to bm divided by s power n plus a1 s power n minus 1 and so on and so forth up to an. And from our previous slide we have shown that x of s by u of s is nothing but g of s, which is the Laplace transform of the impulse response, and therefore by comparing these two equations we conclude that g of s is essentially equal to this expression b1 s power m and so on and so forth up to bm plus s power n plus a1 s power n minus 1 and so on and so forth up to an. So what we see therefore is that for the kind of systems that we are interested in this course, our the Laplace transform of the system is going to be a ratio of two polynomials in S. So a certain numerator polynomial and a certain denominator polynomial. Now what more can we tell about the appearance of the transfer function for systems of this kind, linear time invariant systems? Before we uncover the other properties of the transfer functions, let me just define the notion of poles and zeros which emerge from this particular equation. Since I have the ratio of two polynomials as a transfer function, I can factorize these two polynomials and I can essentially write my g of s as some constant k times s minus z1 times s minus z2 and so on and so forth up to s minus zm divided by s minus p1 times s minus p2 and so on and so forth up to s minus pn, where p1 p2 pn and so on are the roots of the denominator polynomial, z1 z2 and up to zm are the roots of the numerator polynomial. Now there is a special name for these roots, z1 z2 etc. up to zm are called the zeros of g of s, for a very simple reason, because at these particular values if I were to compute g of zi, where I goes from 1 to m, I would get g of zi to be equal to 0. Likewise p1 p2 and so on up to pn are called the poles of g of s, because at these particular locations if I were to compute g of pi, I going from 1 to n, I would get infinity. So at these particular locations g of s blows up. So these are z1 to zm are called the zeros and p1 to pn are called the poles of the transfer function. Now is there anything more that we can say about the structure of the transfer function for linear time invariant systems? It is possible to do so, but to uncover these additional properties we have to appeal to a couple of theorems that relate the time domain response to the transfer function of the system. The first theorem is called as the initial value theorem. I state the theorem here without proof because you are expected to have come across this theorem in one of your preliminary courses on control systems. If you have not come across this theorem, the proof has been provided in the notes and is also indicated and is also available in the textbooks to which we have referred in the notes. So, the initial value theorem states that if I have a signal u of t, then in the vicinity of time t equal to 0, u of 0 plus, I have this relation that the value of the signal at the time at the time t equal to 0 plus is equal to limit s tends to infinity s times capital U of s. So, where capital U of s is the Laplace transform of the signal u of t. Likewise, there is one more theorem that allows us to predict the final value of a signal from its Laplace transform u of s without actually having to obtain the inverse Laplace transform, and that is called the final value theorem. I state this theorem also without proof. So, u of infinity, which essentially means that limit t tends to infinity u of t, is equal to limit s tends to 0 s times u of s, where u of s once again is the Laplace transform of u of t. However, the final value theorem needs to be taken with a pinch of salt, because this theorem is valid only for those signals u of t for which the origin s equal to 0 is within the region of convergence of that signal. In other words, the point s equal to 0 should be a point at which the integral the Laplace integral has a finite value, is within the region of convergence for u of t. Hence, it is not applicable for signals such as sin t or for signals such as u of t is equal to t or e power a t and so on and so forth. If you were to apply it, you get paradoxical results which do not make sense, because these signals either blow up, or in other words tend to infinity as time t tends to infinity, or they are undefined, as in the case of sinusoidal signals. But the reason we get such contradictory and counterintuitive results for these cases is because these signals do not include the origin as part of their region of convergence. Now, let us focus on the initial value theorem and look at its consequences as far as the structure of the transfer function is concerned. The initial value theorem sheds important light on the structure of the transfer function g of s. So, if you let us say assume that you apply a step input to your system, in other words u of s is equal to 1 over s, then the response of your system is going to be given by x of s is equal to 1 over s times g of s, where g of s is the transfer function of your system. So, if you apply initial value theorem to this response x of s, then we would have that x of 0 plus would be equal to limit s tends to infinity s times x of s, and if I were to write it out in terms of g of s, I would have limit s tends to infinity s times 1 over s times g of s, which is equal to limit s tends to infinity g of s. Now, we know that g of s has this particular form. G of s is equal to some b1 s power m plus so on and so forth up to bm divided by s power n plus a1 s power n minus 1 so on and so forth and up to an. This is the structure of our g of s. Now, when we apply the limit s tends to infinity for this function g of s, we have three possible cases. So, we would have x of 0 plus, which is the value of the output x at a time t which is just a little bit after the application of the step input, to be equal to, in the case when m is greater than n, when m is greater than n, you can show that in the limit s tends to infinity g of s would also tend to infinity. So, x of 0 plus would be equal to infinity if m is greater than n. However, if m is equal to n, in other words if the degree of the numerator polynomial is equal to the degree of the denominator polynomial, then we would have that g of s would be equal to b1. And in the third case, when m is less than n, we would have g of s to be equal to 0. Now, what this tells us is that if we apply a step input to this physical system, if m is greater than n, the output of the physical system an instant after application of the step input is equal to infinity when m is greater than n, is equal to b1 when m is equal to n, and is equal to 0 when m is less than n. Now, it remains for us to judge which of these three cases is a practically reasonable case. I am sure you would agree with me that just after application of a step input, the response of a system which is initially at rest has to be close to 0. This is because all systems have inertia and it takes some time before any system can track sudden changes in input. Therefore, all physical systems have to satisfy this condition that m should be less than or equal less than n. However, there are occasions in which the time scale in which we expect our system to respond is much larger than the actual time that the system takes to respond, in which case we can model such a system approximately as one where m is equal to n. In other words, the response of the system is almost instantaneous in comparison with the time scale in which we expect it to respond. So, transfer functions where m is equal to n are called proper transfer functions, and transfer functions where m is less than n are called strictly proper transfer functions. Since we are dealing with physical systems, we are controlling physical systems using electrical circuitry which are again physical systems and so on, all such systems have a transfer function g of s where m is strictly less than n. So, all our transfer functions are going to be strictly proper. However, as I said, in the course of analysis sometimes we can get away by approximating the transfer function to be one where m is equal to n, or in other words a transfer function is a proper transfer function, but this is only an approximation of the physical system which might be valid for the frequency range within which the system operates. Therefore, the initial value theorem has shed an important light on the structure of the transfer function, namely that the degree of the numerator polynomial m has to be less than or equal to the degree of the denominator polynomial. Having looked at the structure of g of s thus far, in the next clip we shall see what further simplifications are possible in the appearance of g of s.